Welcome to another physics lesson in the Physics in Brief series. Today we'll be looking at radioactivity. In this lesson, we'll be defining radioactivity. I will explain what ionizing radiation means. We will mention and state the properties of ionizing radiations. We will explain natural and artificial radioactivity. Let's get started with ionizing radiation. What does that mean? Now, in the nucleus of an atom, just as we discussed in a previous lesson, atomic physics, if you've not seen that lesson, please check the YouTube channel, David Uluwadara, on YouTube. There's a lesson there. The title is Atomic Physics. You would learn a lot about how the atom is constituted. So from that lesson, we already saw that the nucleus has the protons and the neutrons in it. We also saw that the protons in the nucleus are held together by a nuclear force, which is strong enough to withstand the electric force repelling them. We know that protons are positively charged, and according to the law of charges, we know that when things have the same charge, they are supposed to repel each other. But for some reason, protons do not repel themselves in the nucleus. And that reason is because there is a higher nuclear force that is able to hold the protons together, and that nuclear force overpowers the electric force that should have repelled them. So the presence of neutrons in the nucleus affects the balance of these forces. So if you have too many or too few neutrons, it could make the nucleus unstable. An unstable nucleus would disintegrate or degenerate or decay, if you like, giving off energy. And in the process, it could also give off alpha or beta particles. Now, when this unstable nuclei decays, it also gives out ionizing radiation. Ionizing radiation is what causes them to gain or lose electric charge and form ions. So these ionizing radiations, they are the ones that interact with surrounding molecules. And there are three types of ionizing radiations. We have the alpha radiation, the beta radiation, and the gamma radiation. Alpha radiation gives off alpha particles, as the name implies. And alpha particles are essentially helium molecules. Helium. Remember that helium is one of the elements, actually element number 2 on the periodic table. So alpha particles are helium molecules, meaning that they have an atomic mass of 4, 2 protons and 2 neutrons. They also have a charge of +2 because these helium molecules given off in alpha radiation do not have electrons. They don't have electrons. Under the lesson atomic physics, we already said that an atom is stable because the number of protons and the number of electrons are usually the same. So the atom is electrically neutral. But for the helium molecules given off by alpha radiation, they possess no electron. So they have 2 protons which are not balanced by any electron. That's why they have a charge of +2. So this is the alpha particle that is given off under alpha radiation. Alpha particles have a high ionizing power. A high ionizing power. What that simply means is that they can easily interact or easily mix or be absorbed by surrounding molecules. So alpha particles have a high ionizing energy, high ionization energy. This causes the alpha ions to form rapidly, and then the energy is depleted. It's like you have a particle that's supposed to probably travel a distance, but in the course of its journey, it's interacting with every other molecule it sees along the way. That's a form of distraction. That's a form of energy sapping distraction. That reduces the energy it should have had to travel. So that depletes its energy, and then it does not allow it to travel as far as it normally would have if there was no interaction. So alpha particles have a short range. They don't travel more than a few centimeters in air. and they also have a short penetrating power. So in other words, alpha particles have a high ionizing power but a short penetrating power. They can be stopped by a few millimeters of paper. You just put a few millimeters of paper in front of an alpha particle, the alpha particle will get stuck. Now, the second type of radiation is beta radiation. Beta radiation gives off beta particles. Beta particles are fast-moving electrons ejected by a decaying nucleus. Now, the question will be, how can a nucleus have an electron? We already said a nucleus has protons and neutrons. So where is the electron coming from that is now being ejected? Now, beta decay takes place when a neutron in the nucleus decays. So the neutron, one of the neutrons in the nucleus decays. And when a neutron decays, it forms a proton and an electron. Now, the nucleus is a house for the proton, so proton will stay. But the electron cannot stay in the nucleus, so the electron is ejected. This electron is what is ejected at high speed and is called the beta particle. Beta particles are lighter, they are faster, they are less ionizing, and therefore they are more penetrating than alpha particles. Beta particles have a charge of -1, and to stop beta particles, as we said that they are more penetrating, so they will penetrate a piece of paper that you will have used to stop alpha. To stop beta particles, you need a thin aluminium foil at least. Now, the third kind of ionizing radiation are gamma rays. Gamma rays are not particles, they are rays. So they have no charge, they have no mass. They are electromagnetic waves with short wavelengths. Short wavelengths means that they have high frequency, and high frequency consequently means high energy. Gamma rays have the least ionizing power. They don't ionize with surrounding molecules. They don't get distracted, as it were. They don't get slowed down. They don't get bugged by surrounding molecules. They are molecules that you can say face their business and go to where they want to go to without any distractions. Therefore, they have the most penetrating power. These pictures give an illustration of what a radioactive decay looks like. On the diagram on the left, you have the kinds of radioactive decay that you could have. We have the alpha decay, the beta decay, and the gamma emission. As I said earlier, alpha particles are helium molecules. So if you see under radiation emitted column, we have the alpha particle there. Helium has an atomic mass of 4, is put up there. We have already under atomic physics explained how atoms are notated. So if you're still confused, please check that video out. So we have an alpha particle with an atomic mass of 4, that is the one that is a superscript, and the subscript is the atomic number, that is 2. Beta particles have negligible mass, so the atomic mass is 0, but they have a charge of -1, So that is why we have -1 as a subscript. Gamma ray, as I said, they are not particles, so they have no mass, no charge. Now for the generic equation, when an alpha particle decays, when a radioactive element decays under an alpha decay and forms a new particle, the new particle that is formed, the atomic mass of that particle will be reduced by 4 compared to the original particle, and the atomic number will be reduced by 2. That's why under generic equation for your alpha decay, we can see that on the product side, we have A minus 4 as the atomic mass. So for an alpha decay, the atomic mass will be reduced by 4. Atomic number will be reduced by 2. These 4 and these 2 are what goes to the helium molecule. So the atomic number that was reduced by 2 is what gives the atomic number of 2 to the helium molecule. And the atomic mass that was reduced by 4 is what makes the helium molecule to have the atomic mass of 4. So invariably, we are saying that under radioactive decay, the sum of atomic masses on the reactant side, that's the left-hand side of that arrow, must be equal to the total sum of the atomic masses on the product side. And the same thing should happen for the atomic numbers. The same thing also happens for a beta decay. So for a beta decay, because the beta particle has no mass, so the new element formed or the new substance formed still has the same atomic mass as the reactant, as the one that decayed. But the atomic number will increase by 1. The atomic number of the new element formed will increase by 1 when compared to the atomic number of the element that decayed. Why is that? Because that increase by 1 is going to account for a shortfall in the atomic number of the beta particle. Remember that the atomic number of the beta particle is -1. So by the time we add 1 to the atomic number of the product element, and then we now subtract the 1 from the beta particle, it will give us a balance of Z that we have on the reactant side. And of course, for the gamma emission, no particles, no mass is emitted, no charge is ejected, no particle, it's just a ray. So the same atomic number and atomic mass that you had on the reactant side for the reacting elements is what you will have for the product that was formed. So on the right hand side of the equation, we also have examples of equations like that. The first one up there is a beta decay. Carbon-14 decayed to form nitrogen, and it gave off a beta particle. If you look at the atomic masses, on the reactant side, the decaying element is carbon-14. It has atomic mass of 14. If we add the two atomic masses on the product side, we have 14 plus 0. That still gives us 14. So there's a balance. Now the atomic numbers. Atomic number of carbon is 6. But the atomic number of the nitrogen that was formed is 7. Now, if we subtract the atomic number of the electron, the beta particle that was formed, if we do 7 minus 1, we still get our 6 back, which balances what we have on the product side. The next equation is that of an alpha particle. As I said, an alpha decay gives off an alpha particle, which is a helium molecule. So we can see that while the atomic mass of uranium is 235, on the product side, we have the atomic mass of helium as 4, atomic mass of thorium as 231. If we add that, we still get 235. That's a balance. Do the same thing for the atomic numbers, you have a balance. So whenever you are writing nuclear equations, you must keep this in mind, that the sums of atomic numbers and atomic masses must balance on both sides of the equation. And then we have another illustration right down there to show you how these equations or how these decays occur. Here, these pictures illustrate or give us the comparisons between the properties of radiation. For alpha particles, we already said the symbol is the alpha sign, the Greek letter alpha. For beta particles, the symbol is the Greek letter beta. And then for gamma rays, that's the Greek letter gamma. Alpha particles are helium molecules. Beta particles are fast-moving electrons. Gamma rays are just rays, they are not particles. The charge of an alpha particle is +2. Charge of a beta particle is -1. Gamma rays have no charge. Alpha particles have minimal penetrating power. They will not even penetrate the human skin. Beta particles have medium penetrating power. They will penetrate skin and penetrate tissues slightly. But gamma rays have the deepest, highest penetrating power. Now, as this penetrating power increases from alpha to gamma, alpha being minimum, gamma having the maximum penetrating power, so also ionizing power reduces. So the particle with the highest penetrating power has the least ionizing power, while the particle with the highest ionizing power has the least penetrating power. So comparing our penetrating power of radiations, we can see the alpha particle being stopped by a paper, it couldn't go through. The beta particle went through a paper but was stopped by an aluminium. And the gamma rays went through paper, went through aluminium, and a large percentage of them were stopped by the lead. Only the most energetic of them were able to pass through the lead. That is how ionizing radiations can be stopped. Now let us look at how to define radioactivity. Radioactivity is the spontaneous decay of the nucleus of an atom. Radioactive elements spontaneously emit radiation from their nucleus. Examples of radioactive elements are radium, radon, ionium, and we have quite a number more. The phenomenon of radioactivity was discovered in 1896 by Henri Becquerel, who was a French physicist. He found out that uranium gave out some rays that could penetrate through thick black paper and affect a photographic plate placed on the other side. That's why radioactivity is measured in becquerels, because he was the one that discovered it. Now we have another unit also, that's the sievert. The sievert is the unit for measuring ionizing radiation exposure in human bodies. So as humans, we are exposed to some measure of radiation. We have looked at that, and we'll look at that under background radiation. We are exposed to background radiation or radiation from different sources. Now the measure of our exposure, how much of radiation we are exposed to, is measured in sievert, which measures the amount of energy absorbed in a human's body per unit mass. Let's look at types of radioactivity. Types of radioactivity. We have two types, natural and artificial radioactivity. As the name implies, natural radioactivity is when the radioactive element disintegrates on its own. It disintegrates spontaneously over time. Artificial radioactivity is a kind of radioactivity that is brought about artificially by bombarding a non-radioactive material with radioactive particles. So if I have maybe carbon, for instance, or any other material, and I want to force it to decay, I can bombard it with maybe a neutron or a positron that could force it to decay. That's an artificial radioactivity. Now, radioisotopes or radioactive isotopes are isotopes that are made artificially by bombarding elements with protons, neutrons, or electrons. As I said earlier, we all are exposed to ionizing radiation, background radiation. So what is background radiation? This is low-level ionizing radiation produced all the time. They may be found from natural sources like rocks within the Earth's crust, or even cosmic rays from space, or artificial sources like the radioactive tracers used in medicine and industry, the isotopes used in cancer treatment, or even power generation in nuclear plants. Nuclear plants may give off some measure of radioactivity or background radiation to people surrounding there. That's a background radiation that they cannot avoid. So we all are exposed to some form of background radiation or the other. But the level is low. They are low, they cannot pose harm to us. So background radiation does not pose harm until it gets to a critical level when it becomes dangerous. But background radiation is a radiation that is at a very low level and doesn't pose harm. As I said earlier, sources of background radiation may be from cosmic rays, radiation from rocks, radon gas. Radon gas is a gas given off by rocks in the Earth's crust. Radioactive sources in the body, even medical sources, nuclear plants. And then the knowledge of background radiation is useful because when we have people who work with radioactive materials, they are exposed to radiation. Now, they already have a background radiation that they are exposed to. So when the measurement of the amount of radiation they should be exposed to based on the material they are working with is being done, the amount of background radiation in that environment must be factored in. If, for instance, a scientist working on uranium is still safe being exposed to maybe 20 microsieverts of uranium, you cannot now just say that until he gets 20 microsieverts from uranium, that's when he is safe. Don't forget that 20, you must already factor in the fact that he's probably already exposed to 5 microsieverts from the surrounding. So the amount you can allow him to be exposed to from the uranium he's working with is maybe 15 microsieverts. That's why knowledge of background radiation is important, so that we are able to factor in the amount of radiation already in us before we now know what amount of radiation we can afford to be exposed to when working with a radioactive material. So here we end the lesson and we have a homework. Our homework is basically about writing the nuclear equations. Technetium 99M. 99M is an isotope of technetium. It still has an atomic mass of 99 anyway. It decays to form technetium 99, giving off gamma ray. As I said, gamma ray is just an EM ray. Doesn't have a mass, doesn't have a charge. So write the equation for that. Also write the equation for uranium-238, which decays to form thorium-234. You may need to go and find out what the atomic number for uranium-238 is to write that equation. What kind of equation is that? And then describe briefly the alpha particle, beta particle, and the gamma ray. As I said earlier, I said that when you are writing nuclear equations, the sum of atomic masses and atomic numbers on the reactant side must balance those on the product side. So this is the end of the lesson. Thank you for being a part of this lesson. May I remind you also to subscribe to this YouTube channel, David Oluwadara, so that you can get notifications when new videos are posted. Thank you. See you in another class.